We saw in the previous video how to draw right triangles that are similar to each other with an altitude and how those can be used to solve some problems. And we also saw how to sketch those triangles to find proportions and set up and solve those proportions. It turns out there are a couple shortcuts for doing so that are well known that you should know. The first is called this geometric mean altitude. Recall from before, the geometric mean of two numbers is some number x that satisfies this proportion. So the first number compared to the geometric mean is equal to the geometric mean compared to the second number. It turns out that geometric means show up in these similar right triangles. In one place, if you have the altitude, I'm going to call that big A, the altitude. The altitude ends up being the geometric mean of the two segments that make up this. So maybe we'll call them the two parts. How about part 1 and part 2? What this says, if you draw out the similar right triangles and you compare them, you always get this proportion, that one part compared to the altitude is the same as the altitude compared to the other part. So this can be useful if you don't want to take the time to draw out right triangles and see visually the corresponding parts. This, if you recognize that you're looking at one of the things you know or are looking for is the altitude, and you know the lengths of the other of the two parts of this hypotenuse that have been divided, then this proportion will always be true. In the same fashion, the legs or the original sides that are not the hypotenuse of the right triangle also are geometric means of two things. If you look at a leg of a right triangle that's been divided by a hypotenuse by an altitude, then it turns out that when you redraw and identify the corresponding parts, that if you look at this part that's adjacent to the leg, adjacent meaning touching, so this part that's if I'm looking at the leg AC, then this part of the hypotenuse from D to A is adjacent to this leg because it eventually touches this part. That this part and the hypotenuse, or the entirety of this hypotenuse, the whole thing, that the leg is the geometric mean of this part and the entire hypotenuse, which is a fancy way of saying that this ratio will always be true. That if you compare the part of the hypotenuse to the leg, that's the same as comparing that leg's length to the whole hypotenuse. So again, you don't have to use either of these two theorems, but this can cut down some time in terms of not needing to just keep drawing and drawing out three triangles like we did before. We can use this to hopefully make our solving lives a little bit easier. So I'm going to apply these a couple times to show you how they work. In this triangle, it's a right triangle with an altitude drawn in, so there's some similar triangles here. I could label these corners, draw a bunch of right triangles, and then identify the corresponding parts. Or I recognize that the altitude is the thing I don't know, but I know the lengths of the two parts of this hypotenuse has been broken into. And according to the first theorem, that I think that this proportion should be true. That this part 10 compared to the altitude is the same as the altitude compared to the other part. Or better yet, if I cross multiply, x times x is x squared. 4 times 10 is 40. So x is the square root of 40. Or if you simplify this square root, this breaks down into 4 times 10. So the square root of 4 is 2. I don't know what the square root of 10 is. It's 10. In the same fashion, again, I have another right triangle that's got an altitude drawn in. And I know something about the altitude and the two parts of this hypotenuse. So I think part compared to altitude is altitude compared to part. For cross multiply, I get 8x is equal to 12 times 12 is 144. Or divide by 8, and I get x is equal to 18. So again, I solve each of these without having to go to the trouble of drawing out the triangles in a more elongated process, because I knew that those that theorem of the shortcuts. Here's a couple examples of the second theorem. In this case, I don't know anything about the length of the hypotenuse, but I do know some parts of the hypotenuse, and I also know the length of this leg. And since I know the leg, this immediately tells me that I could use that leg theorem. Specifically, that the part of the hypotenuse that's adjacent to this leg, which in this case is 3, because 3 touches this side that's y, that this part compared to the leg is the same as, or is proportional to the leg compared to the entire hypotenuse. And although it's not stated, I can easily calculate it. 3 plus 8 is 11. So part to leg is leg to whole hypotenuse. Or do some cross multiplying. Y times y is y squared. 3 times 11 is 33. So y is the square root of 33. In this problem, it looks very similar. I don't know the altitude, but I do know a leg, and I do know a part of the hypotenuse, and actually I have an expression for the whole hypotenuse. So I think this proportion should be true, that the part compared to the leg should be the same as the leg compared to the entire hypotenuse. In this case, that's z. Or cross multiply, you get 16z is equal to 27 times 27, which according to my calculator is 729. So I get z by itself by dividing by 16. I get z is equal to, well, 729 over 16, which is the exact answer. That's on my calculator, that's about this kind of not great decimal, 45.5625. I think this exact answer is fine enough. Lastly, a common thing to be presented with is a triangle with just a right triangle with an altitude drawn in and just a bunch of missing parts. We need to find what all the unknown sides are. There are a lot of strategies you can use. Since these are right triangles, the Pythagorean theorem should work. If you can identify a triangle and you know 2 of the 3 sides, then you could use the Pythagorean theorem to find a third. That's useful. But you could always draw similar triangles. Or you could use the theorems, those shortcuts that we just saw. Any of these methods, if you have the right setup, you can use. So what I like to do is I'm going to identify, when I start a problem, I'm going to identify one of the variables that jumps out at me from one of the methods that I know. That I know everything other than the unknown. Then I'm going to use that method to find it, and then fill in as I go. And then from there, I can use what I know to find the rest of the unknowns. The thing that jumps out to me, in my eyes, is the altitude z, and I know the 2 parts of the hypotenuse. That jumps out at me is that first theorem from today. So I'm going to find z first in this case, because I know that this part of the hypotenuse divided by the altitude, same as the altitude divided by the other part. Or z squared is equal to 9 times 11, which is 99. Z is the square root of 99. If you use a factor tree, you can show pretty quickly that this is 3 square roots of 11. So z is 3 times the square root of 11. If the direction said you could round, then you could type this into a calculator and just round it to the appropriate decimal place. But this exact answer is going to be nice. This is going to be more useful for finding the rest. This tells me that z is really 3 square roots of 11. In this case, you could find both x and y by using Pythagorean theorem if you want, because in the case of this smaller right triangle here, I know a side, and you're looking for the hypotenuse. So you could say a squared plus b squared equals c squared is one method you could use. I'm going to avoid that because I don't really want to have to square and square root as much as I'm going to try to do that as little as I need to, because x is also the leg of this right triangle, and I could use that leg theorem that we just saw to try to solve for x, because I know the part that's adjacent to this x, and I also can quickly calculate the whole hypotenuse, which is 9 plus 11 or 20. So I think I could find x because I know x is the leg. I could say this part that's adjacent to x divided by the leg is the same as the leg divided by the entire hypotenuse. Or x squared is equal to 180, where x is the square root of 180, which works out to be, if you use a factor tree, works out to be, I think, 36 and 5, or square root of 36 times the square root of 5, which is 6 square roots of 5. And lastly, you could apply the same line of thinking to finding y, because y is also a leg of this big right triangle. You know the part that's adjacent to it, 11, and you know the length of the entire hypotenuse, which is 20. So maybe in a similar fashion, I could do 11 compared to y, the same as y compared to 20. Y squared is equal to 11 times 20, which is 220. Or y is the square root of 220. Which, again, using a factor tree, you can show using a factor tree pretty efficiently that this is 2 square roots of 55. Again, if the direction said you could round to the nearest 10th or 100th or so, just type this into your calculator and get it to decimal and round it appropriately. But I think without that, the exact answers, I think, are the best answers.